Hi everyone, welcome back. I hope you watched our last video because this is basically a continuation of the last video where we talked about genetic algorithms and we actually defined a few functions for various aspects of this genetic algorithm, for example, to perform crossover, to perform mutations, and then we got a good understanding of what genetic algorithms are. And in this one, let's go ahead and put that to use. Actually, let's go ahead and optimize a scenario, optimize a couple of parameters. Now, in this case, I am going to use a machine learning model. Why not? Because that's what we do. That's what we have been doing for the last 300 plus videos. And if you guys don't know what I'm talking about, hit the subscribe button right now. You have to pause the video, hit the subscribe button, and while you're there, find the thanks button if you're feeling extra generous. Okay, now let's get back to the topic here. I was mentioning that we're going to use a machine learning model, a random forest, for example, to fit certain data to predict an outcome. But that machine learning model is going to be our fitness function, our optimizer, or not optimizer, or objective function, sorry. Fitness function or objective function, whatever you want to call. Now we're going to use that and search the space between certain bounds for each of the parameters that we want to optimize and find the optimal values for those to get the best outcome. Okay, so that's what optimization is. So let's go ahead and jump into the code and I'll explain more as we get into it. And as usual, I am going to share the code that you see on the screen. This is basically a notebook, a Python notebook. So let's go ahead and connect to the Colab, which means all of you should be able to access this. And I have created a CSV file, an artificial CSV file. You can do the same, or you can find some real data. But in this case, this data is basically, we'll understand the data in a minute. So you have like two columns. Mount in Google Drive. Yeah, it's mounting the Google Drive because my data, I stored the CSV in my Google Drive right there. And the libraries that we're going to use are pretty straightforward. And again, pandas, so we can actually read data from CSV and save it as a data frame. Matplotlib for plotting, scikit-learn because our objective function is going to be a machine learning function. So scikit-learn random forest regressor is what we're going to use, and numpy is numpy. So let's go ahead and import that. And I'll import the data and then we'll see exactly what I have here. It should be 3 columns primarily. I mean, let's ignore the first one. We're going to drop that. So biking, smoking, and heart disease. This is a hypothetical cities, let's say villages, towns, whatever, hypothetical communities where certain percent of population do biking. For example, 30.8% are bikers. 10.9% are smokers. So if that's the case, what's the probability of a heart disease? That's basically it. And I have a whole bunch of these values. And first, let's go ahead and fit this to a random forest regressor. I hope you guys know what it is. If not, you'll learn quickly what it is. But like we already established, unnamed 0 is a column that we don't care about. Let's go ahead and drop it. And let's also see if there is any missing values. Nothing. Otherwise, we would fill it with something or drop them. And let's understand the data set here. Again, no matter what job you're trying to do, optimization, machine learning, whatever, pandas or equivalent to pandas, whatever, you pick your favorite library, understanding the data, any library that helps you understand the data, it's crucial. So if you want to call yourself a machine learning engineer or data scientist or data analyst or even a scientist who uses data tools or an engineer, you got to know how to wrangle data. And for that, pandas can be very useful. Yeah, I'm pretty sure most of you know that, but if you are someone new to coding, hopefully you'll take that as a good advice. Okay, so now let's describe our data set. So biking, we have 498 total entries as part of our data. Of those, that's the mean, standard deviation, and all that. So for now, let's actually look at minimum and maximum. Well, in this case, yeah, we do have max right there. So the value goes from 1 to 75-ish, and smoking goes from 0 to 30-ish. Why are we looking at this? Because later on, when we actually do set bounds for our genetic algorithm, we can set them from minimum to maximum, right? I mean, or you can extend the maximum by a little if you want, but typically it's customary to say, hey, my minimum is the minimum in my data set, maximum is maximum in my data set, and the optimal solution lies in between the minimum and maximum. That's the assumption. And is this correlated? Obviously, they should be correlated, right? So what is heart disease correlating with? So it's 93% with biking. Apparently, biking really helps. It's smoking. I mean, it's correlating with smoking 30%. So it's yeah, of course it has an effect, but it's actually correlating with biking. And the negative side means the higher the number, the lower the heart disease. Here it's higher the number, the higher the heart disease. Again, basic data analysis, as you know. Now for defining x is nothing but the input variable. So everything except for the heart disease value, because that's what we are trying to predict, and that's our y. So let's go ahead and do that. I mean, this lecture is about optimization, but I'm just talking you through machine learning primarily because I want to use this machine learning as the objective function. Why use some silly x squared plus y squared equals to something? We did that in the last tutorial. So if you want something simple, watch the last tutorial. Now I'm getting into somewhat real life scenarios. Okay, let's divide our data into training and testing. And let's fit a random forest regressor with about 100 estimators. And I did a few videos on random forest. This is one of my favorite traditional or conventional machine learning algorithms. Like gradient boosting is actually my best, my most favorite. If you want one machine learning algorithm that works on multiple scenarios, and gradient boosting, yeah, don't even think about it. Okay, let's go ahead and predict. Now that the model is trained, fit on our training data, let's predict on the test data and look at some parameters like root mean squared error. So there you go, RMSE is there, and it makes sense to actually plot actual versus predicted. Very nice linear relationship right there. I'm happy with that. That tells me that the model is doing okay. Various ways of assessing the quality of model. That's not what we're doing here. Okay, so and of course, if you're using something like random forest, you can also get like the feature importances. In this case, biking is the most important feature. Smoking, we only have two. In some cases, you may have many, right? So we'll do those exercises in the next couple of videos. I'm just showing you a few things that I normally do when I work with data. And I'm more of a visual person, so even though it gives me some sort of a accuracy factor, RMSE or something, I love to see some sort of a plot and infer something about it. Okay, now moving down. So now that we're satisfied with the model, we know that, okay, we have the model. Now let's actually fit the entire data to this model, like x and y. Yeah, I'm just fitting. This is not necessary. I just want more data, so I'm just fitting it. And from now on, model underscore full is the fitness function I'm going to use to optimize these two parameters. I hope that makes sense. Yeah. So you can use, again, if you know that any other function defines the relationship between the input, and the output, that can be your objective function, fitness function. I don't know that, so I fit a machine learning model and I'm like, hey, I'm going to use this as my objective function. That's all I'm trying to do. Okay. Now comes the genetic algorithm, right? So what do we do? First thing first, let's import the required libraries. The next thing, if you remember from the last tutorial, we start off by defining an objective function. And in the last tutorial, we defined, I think, x minus 7 squared plus y minus 10 squared, which basically means the solution should be 7 and 10, right? So when you're minimizing that. But in this case, we are our objective function is nothing but our model.predict. Is the objective function, and we are trying to when you plug your input values, in this example, when you plug x in there, by the way, the x is a list of both the smokers, percent smoking and percent biking. Yeah, so that's our input. When I plug my input right there and do model.predict, I get some result, and that result is something that I am trying to minimize, so I put a negative sign right there. Let's go ahead and run this objective function. Next, decoding. Again, I explained this quite a bit in the last video, where we say, okay, we are representing these by something like genes, right? So we have binary values, 0, 1, 1, 0, 1, 0, 1, so on. We're generating a binary string of how many ever, whatever the length is. For example, in our case, we are going to use 16-bit. So you're generating a 16-bit binary string for each parameter that we are trying to optimize. So in this case, we have two parameters. So we have 16, 16, 32, right? So the length of 32. So that's what we are generating. So, and bounds is basically, what are the bounds? In our example, I recommend actually going the minimum value for each of these parameters we're trying to optimize, and the maximum value. These are the bounds. So we'll define that later, but that goes in as an input to the decode, because whatever the value that it is decoding, it needs to be within our bounds. Which means we need to know what the minimum is, maximum is, and normalize the value that it finds here, the binary value that we are converting to an integer, into between those bounds. If none of that made sense to you, you probably haven't watched my previous the last 2-3 videos. I recommend you going back and doing that. But I'll try my best to make some sense out of this. Okay, and the bit string is the string I just mentioned, the 32 or 16, whatever, how many ever zeros and ones that you have, it goes in as input, and this function converts that into a number that falls between that bounds, whatever the bounds that we define. Okay, so yeah, we are taking this string and we are dividing that into how many ever substrings. In this case, the substring would be 16 and 16. And we are converting that into characters and characters into an integer. And that is the integer that we want, but not as is. We need to normalize that. And how are we normalizing it? By taking the bounds and squeezing our integer into that bounds. And that's what decoded value is. I recommend running this line by line and trying to get a better understanding of the case. Now, once you have that decoded part done, now let's get into the genetic algorithm steps. Step 1, select. Step 2, crossover. Step 3, mutate, right? And run them in an order. So selection itself, you have a population. So let's say we create like a population of 100 candidate values for our smokers, and 100 candidate values for our bikers. When I say bikers, it's biking percentage. Yeah, the percentage values. And then a score goes in. We need to take each of those, calculate what the score is. We know how to calculate the score. It's basically, oh, sorry, where am I? Why am I going back? Sorry about that. Okay, let's make sure we are here. So yeah, I randomly clicked something. But yeah, so I got carried away. I was talking about, okay, how do we get, so we are done with this part, but how do we get the selection process done, right? So the decode is done. So I was talking about this one, the objective function. When you actually plug your input value, whatever the input string is, into the objective function, you get some result. And that's basically the fitness criteria. And that's exactly what the scores are right there. So what is that score? Okay, so as part of the selection itself, you're actually randomly selecting something from total population, and then you are using a tournament among k randomly selected individuals, which means, okay, you have 100 population. Of those, you say, okay, just take the 10% of these population, and that 10% is the top 10 of, or top 10% when it comes to scores. You look at the scores and you're like, okay, you want the top 10%. And then what else? So that's that part. And once you do that, for each of those, you are going to select from those, you're going to select the parents, 2 parents, right? And those 2 parents are the ones that go into the crossover right there. Again, when I paused there for a second, I was thinking about, should I go into the depth again and bore regular audience, or should I, for people watching for the first time, should I explain this? So excuse my pauses there, but let me move on. Okay, you have you use the selection criteria up there to actually select the top 2 parents, and those 2 parents are the ones that are used to do crossover, so you can get the child, and that child actually gets mutated to get your result. So that's where it is, and R cross is basically the crossover rate. What percentage of these values do you want to perform the crossover operation? So the crossover is basically, if you just randomly, if it is 10%, pick 10% random, and then just swap between the parents, the values. Yeah, whatever the values are. And then you're performing mutation. What it returns is 2 children, right? So that's what we are returning right there. And that children, if you want to mutate it, the bit string actually goes right there. And what is the rate of mutation? The rate of mutation, again, typically is 1/m, where m is total number of features that we are working with. Okay, So let's go ahead and yeah, it's very straightforward and simple. You're going to randomly flip one of the values that you have in your list right there. So if it's 0, 0 to 1, or 1 to 0, basically that's what the mutation is, and at what rate. Like, it's very low rate that you define up here. Once you have all of those, did I run that? No. Let's go ahead and run that line. Now we are putting everything together, where you have the genetic algorithm, where the objective function goes in, the bounds like lower and upper limit, what the bounds are for each parameter that actually goes in, number of bits. Is it 16 bits that we have our binary number encoded as, on number of iterations, which is nothing but number of generations that you would like to go through for this genetic algorithm, how many population, what's the population size right there, crossover rate, and mutation rate. If you think about it, very simple and straightforward, all of this. Yeah, so let's go ahead and run this, and all of these go in, and what happens? I mean, it's again pretty much sequential. So you generate your population. Let's say you have 100 digits. Yeah, sorry, 100 people population, each of the size, whatever the size that you define, and values between 0 to 1, right? 0 or 1, that's what this is. And then you create, you calculate the objective function, you apply the objective function, but to apply the objective, you need a decoded value. You cannot just plug 0, 1, 0, 0, 0, 1, all that into your objective function. Then your random forest doesn't know what to do with it. It actually requires real numbers. Real numbers, you're converting that using our decode function that we defined first, and then using that decoded value, you're applying the objective function, and then you're actually getting your the best solution by looking at the objective function, right? So there you go. And then for each generation, you're actually decoding it. And on the decoded, again, you're looking at the applying the objective function, looking at the scores. And once you have the scores, then you're looking at your best ones. And I'm printing, while we are doing this, we are going to print our best ones. And then the selection happens. You select the top two, and then you send those top two as your parent 1 and parent 2 right there. And crossover happens. And once the crossover happens, mutation may happen depending on the probability. And you have the children, and that is basically what you're returning right here. Best and best eval. Okay, so that is done, and now let's go ahead and run all those functions. Basically run this one. Yeah, run the genetic algorithm with these inputs, where the bounds are. For biking, the bound would be the minimum of the biking, and the maximum for smoking, same thing, minimum and maximum. You can define your own numbers if you want. Yeah, and number of iterations, generations 10, 16-bit, 100 people, crossover is 90%, and mutation rate is 1 over these values. Let's go ahead and run it, and you'll see that it's running, whatever the warning it's throwing up there. And once it's done, let's go ahead and decode the value, the best value. And because the best is what we are returning, right? While it's doing, we can, the best is what we are returning along with the score for each of these. So let's go ahead and print. So the result is 1.35 and 28.54. Obviously, you can imagine the lowest when it comes to smoking, the highest when it comes to biking, with a score of 20. If that's the case, that is going to be the heart disease. Not a spectacular example, but some example that kind of gives you the feeling for real life scenario. Now, the question is, do you need to do all that coding if you want to do your own genetic algorithm? It does make sense to kind of do coding for fun, but if someone already put together enough energy into creating a library that probably is optimized in terms of both computation and data handling, why reinvent that? So one of those libraries is genetic algorithm library, and you can I mean, I provided the links right here. I'll also provide links down as part of the description. So let's go ahead and install that genetic algorithm, because it does give us quite a few options, not just one algorithm, but there are a few easy to use, let's say. Okay, so now that it's installed, let's go ahead and import genetic algorithm module and assign an alias to it. This is every little line right there. So from this genetic algorithm, we are going to import genetic algorithm. I think they have a few other meta-heuristic algorithms as part of this package, but go ahead and check it out. Okay, so we are going to import this as GA, and then we are going to do exactly the same as before. We define our objective function, exactly the same function, nothing different there. except we are using a pre-configured library, which means we don't have to define our own crossover and all that stuff, but we need to kind of define the boundaries, right? So the boundaries is, in this case, they accept boundaries as you can see, an array of minimum maximum. Previously, I think we did list of lists. If I have to go back and check, but yeah, in this case, they accept array of minimum maximum for each of the parameters that we have. So that's how it is in any genetic algorithm. Define the boundaries, how many of our parameters, go ahead and plug that as your input. Okay, so there's that. And we are going to define all the parameters required for this genetic algorithm. And most of this should be relatable now that you have watched 2-3 videos, I assume you did, of mine. So first of all, maximum number of iterations is like generation that we have done. Population size is population size. Mutation probability, straightforward. We know what that is. Elite ratio is what ratio of the entire population do you want to pick as the top. And crossover probability, you know what that is. Parents portion, I have to look what parents portion is exactly. And crossover type, apparently they give a few types of crossover, like uniform crossover and a few other crossovers. And maximum iterations without improvement, like, okay, you can set another hyperparameter where you can define how many, even though it's not improving, how many iterations do you want to do. And that's there. And now we are defining our genetic algorithm model. So our GA model is the function. You need to supply the input function. Objective function, we defined that. There you go. This is our objective function. It doesn't matter what the objective function is. I mean, we are using a random forest trained model as an objective function. It just needs to take an input and it needs to provide an output that that you can use as fitness. That's it. Objective function, dimension, we have 2 variables. So that's our dimension variable type. In this case, we have real variables. I mean, obviously, these guys have done a lot more than what we did in the first few functions. That's why I think you should use this, yeah? And yeah, and then go ahead and run it with all of these inputs. Let's go ahead and run it. And again, it should do a similar type of computation here. That's what, I mean, we just saw coded our own backend, right? So our own functions up there. Now it's actually using its, and come down, and obviously it's giving you a very nice visual right there. After the second iteration, it looks like you got to the solution. Of course, this is a simple one, but you may have complex ones later. There you go. So the biking 1.2, smoking, very similar result as before. So the essence here is, I hope with this video you understood exactly what genetic algorithms are, and especially in the context of optimizing a function. It doesn't matter whether it is a random forest like machine learning function or any other function. And more importantly, I want you to understand the importance of using pre-configured libraries, the importance of actually coding it yourself so you know what's happening. That's the only way you know. When you code every line, you're like, this is exactly what's going on. You need to get to that aha moment and then just screw that code. Just go and use something that someone else has written in a much better way probably than you can ever do, or I can ever do. Okay, guys, I hope you really enjoyed this video. If so, go ahead and hit the like button, leave the comments and blah, blah, blah. Hit the subscribe button, of course, and I'll see you in the next video.